In this video, we will take a look at angular velocity, which is the angular analog in rotation to velocity that we have in linear land. The definition of angular velocity is almost exactly the same if you say it in words as what you would say for the definition of velocity. All right? You would say that it is the time rate of change. Time rate of change of position if you were talking about regular velocity. The only thing that we do now is we put the word angular. So it's angular position. So we're looking at the change in the angle. That is the angular displacement divided by the change in time. And of course we're going to let that change in time go to 0. If we don't let it go to 0, then we found the average angular velocity because it's the change in angular position or the angular displacement divided by the change in time. So it looks exactly the same as what we had back in the case of linear land. We had, let me write that kind of to show you, we had velocity was defined as the limit as delta t went to 0 of the displacement delta x, if you would, over delta t. And it was a vector. Well, this new one is a vector too. While theta may not be a vector, as I talked about in the last video, the change is. And that means that omega has direction as well. So that's its definition. The only thing that gets added is the word angular. The units, well, the units come from right here. Now that's in radians, which is a unitless quantity, and this is in seconds, so the units are rad per sec. Radians per second. Now, in the previous video, we talked about the fact that angular position was connected back to regular position, and it was by the radius, which gave the regular position its units of meters. The omega is related to the tangential speed an object has running on the circle. That velocity is going to be equal, or speed, I'm leaving off the direction here, is equal to omega times the radius. Very important formula for you to know. I'd say memorize. Now, how did we get that? It turns out that all we did is that we just went ahead and used these type of definitions. We found the change in x, which is in our case for going around the circle, s, and we divided that by time, and we ended up with this equation. So again, rads per second, but then you multiply by meter, you get meters per second. The radians go away. Very similar to what we had in the last video, where we had length s was equal to theta times r. So when you go from angle land into linear land, you take the variable and you multiply by r. Angular velocity is a vector. So therefore, it really should have some sort of direction. Well, you can spin a wheel one way, you can spin the wheel the other. Clockwise and counterclockwise might make sense. It's hard to show you on paper, but the reason that doesn't happen is that if you spin your arm, swing your arm, and you look at it from one direction, get two friends, one stand on one side of it and the other stand on the other, and spin your arm. One of them will see your arm moving clockwise. The other will see it moving counterclockwise. So whether you say that your arm is spinning clockwise or counterclockwise depends on where you're standing. So we came up with a way that didn't depend on where you're standing. It's called the right-hand rule. And it requires you to use your right hand. Now, that means if you're right-handed like I am, you have to put your pencil down if you're going to do the right-hand rule when you're working problems. If you don't put your pencil down, you'll be using your left hand. The right-hand rule says this: take the fingers and wrap the fingers of your right hand in the direction of rotation. Your thumb points in the direction of the angular velocity. Make that easier to read. So if you have an object spinning like this, you wrap your fingers in the direction of this little gray arrow. And when you wrap the fingers of your right hand in the direction of that gray arrow, your thumb will be pointing upwards. That's the direction of omega. That's the direction your thumb's going to point when you wrap your fingers of your hand like that. If you use your right hand. If you use your left hand, you'll get the direction backwards. You need to go to France. They use the left hand rule and change all the formulas. Alright, so wrap your fingers, your thumb, right here, your thumb points up. That's the direction of omega. If the disc is spinning the other way and you wrap your fingers, you can't turn your fingers that way. You have to turn your hand over and wrap your fingers. Your thumb will point down. And so when you do that, your fingers are pointing that way. Obviously not nearly as good a hand this time. I should have quit while I'm ahead when I did it right once. Nah, don't even like that. I'll let you draw it. And it's going to be like this. Terrible drawing. So it's important to do this because of the clockwise and counterclockwise are ambiguous. Now when you lay something on paper in 2 dimensions, like on your textbook, you can kind of get away with the doing it where you say it's clockwise and counterclockwise. And we'll do that some. But certainly it's not true in most things that people who do science and engineering and such, because they deal with 3-dimensional buildings and 3-dimensional walls and spaceships that are 3-dimensional. They don't just deal with flat things. So let's take an example. You have an object. This guy's going like this. There's the velocity. Notice that vector v is like that. There's r. That r is pointed like that. If you wrap your finger in the direction that the little blue particle will go, you'll find that it points out of the board. Because I can't draw that with an arrow, I usually draw it like something like this. Let me explain to you how that works. A normal arrow would have something like this. It'd have an arrowhead and it has some feathers. If you're looking at this, I see the outside of the arrow point. That's this part right here. And that's what I draw. But I also can see the tip. If I draw the tip, I put a dot. That is a bad way to look at arrows. That means that arrow's coming right at your head. That's out of the board. And that's the way my thumb pointed when I wrapped my fingers around this circle. If you see it going into the board, you would again see this part of it, which would be the circle, but you'd see these feathers. And we draw those feathers usually like this. Now let me change colors so it's easier to see. So that's the feather. That's into the board. That's okay. It's not going to hit you in the head. It's going away from you. So sometimes in textbooks and elsewhere, they will draw these type of symbols to indicate into the board or out of the board. And that really pretty much covers everything that we need to do about velocity. I might say one other thing, I guess, while I'm here. If you do it with x, y, and you try to draw it where you can see the 3 dimensions, that would be z. When you wrap your finger in from x to y, your thumb will point in the direction of z, which will be out of the board. So if you made your axis like that for this problem, then this out of the board would be k hat, the z direction. Because you're wrapping it with your right hand, these are known as right-handed coordinate systems in mathematics and in physics. If you had used your left hand to do this, your thumb would point the opposite direction, and they'd be called left-handed coordinate systems. In Western countries throughout, as well as China, Japan, and so forth, and other places, there's agreed upon that we will use right-handed coordinate systems when describing physics systems or engineering systems. So we always use right-hand coordinates. All right, I'll talk about angular acceleration in the next video.